All right, welcome. We're going to do a tutorial and a lesson on points of inflection, inflection points, and concavity of a graph, and how we do some analysis using the first and second derivative to help us figure this out. So, without further ado, first thing we probably want to know is what are points of inflection and concavity? Well, if you want to pause this, this is kind of the definition. You can find this on the web or in most calculus textbooks, and what we have is the definition of concavity. Concavity is defined where a function is concave up if f prime is increasing on an interval. That's known as concave up. Concave down is when f prime is decreasing on an interval. In other words, if a graph arcs like a U, so if we had a function like so, and you notice that on this function, all right, f prime is increasing, that means the rate of the function is increasing. This would occur, all right, at what we say concave up. And how do you identify this on f? Well, as it says, u is concave up, so right here, all right, at this point, you notice how our curve begins to go up. That's what's known as concave up, so u. Okay, concave down is like a golden arch at McDonald's, or if you have this right here, you notice that it was a frown. I say concave down was a frown, and you can see that it's kind of going down there. Okay. Now, how do you identify concave up and concave down is? Well, we can figure out when f prime is increasing or when f prime is decreasing. But more importantly, we can also identify this by using the second derivative. Okay. The second derivative, if we notice that f prime or f double prime is positive, we will know that it is going to be concave up because that is when f prime is going to be increasing. When f double prime is negative, that's when it's going to be concave down, and that's because that's when f prime is decreasing. So we're kind of using like the first derivative test to help us figure out where, all right, things are concave up and concave down, like we did with max and mins for the first derivative test. Now, finally, where does all this change? Well, when you realize that f prime double prime equals 0, well, that's where we have neither concave up or concave down. But actually, that's also where we can be located points of inflection. Points of inflection. Points of inflection are defined where neither, all right, on a graph where there is a change in signs. Okay, change in signs. So when f double prime equals 0, or where it's undefined, that's a possible point of inflection. Points of inflection also need, all right, to have where f double prime changes signs, because that's when f prime changes from increasing, decreasing, and so on and so forth. So essentially, points of inflection are like the critical points, all right, of the second derivative. Okay, critical points of the second derivative, and that's what we're looking at. All right, so that is a definition. You can pause this, you can write these down, but we're going to use these definitions to help us justify and identify where we have concave up, concave down, and points of inflection. So let's try this out. All right, so here we go. We have our function, okay? We have a function, 4x cubed plus 21x squared plus 36x minus 20. And we're going to identify the points of inflection, and we want to figure out the intervals where the function is concave up and concave down. And then we want to justify our answers, Now, when we're doing this, we want to figure this stuff out. So if you review and look at this, I'm going to actually take out our calculator. So I'm going to pause this and get a calculator ready. So we can look at what this graph is going to look like and then go through the analysis to figure it out. All right. Well, as you can see, there all of a sudden is a graph just pop up out of here. Go to your graphic calculator. I graphed this function, f of x, and I went to zoom fit on a TI calculator, and this is the graph we had. Now, understanding what concave up and concave down are. Once again, when we want to justify our answers, this is what we're looking for. And sometimes when I do this, I try to justify our answers first. What we're looking for concave up, concave down is f is concave up. So we're going to justify our answers first so we know what we're going to be analyzing. Concave up, all right, it's concave up on the interval, all right, or intervals, and blank. Now why? Because what we're looking for is where f prime is increasing. I'll just use a little short notation. or where f double prime is positive. Okay? Now, where does this occur? Well, concave up, if you recall in our previous, just a little while ago, I told you where concave up is where our graph is starting to increase. So it appears, or where our graph has like a little U. Well, looking at this, it appears that our graph is going up, or f prime, where the slopes are increasing, right? Getting somewhere at this point, and then increasing this way. According to the graph, that's what we see. Now, where does this look? Where is this located? Where is this possible point of inflection? All right, point of inflection. All right, we'll find that out in a little bit. But let's continue on our justification. So that's where concave up would be. F is concave down. All right, on the intervals. All right, fill in the blank. All right, because f prime is either decreasing or f double prime is negative. Okay, and that's what we're looking for. We got to figure out when f double prime is negative. All right, that's where it's going to be concave down. Now, right here, you can see that concave down on the graph, f, this is f by the way, all right, is where we have that frown. You can see we have a little tiny frown right there. Okay, and it appears that we have this point where it changes, and that's going to be our point of inflection. All right, that's our point of inflection. So now, the question is, where's our point of inflection? Well, our point of inflection, all right, F has a point of inflection. Appears we only have one, possibly. Point of inflection, all right, here, okay, because that is where, because F double prime changes signs. All right, and that's our justification. So we're going to fill in these blanks. Now, to fill in these blanks, we're going to do a little bit of analysis. Okay, we're going to do a little bit of analysis. So I'm going to take this down here, and we're going to work with this, and then go back up there and justify your answers and so on and so forth. So the first thing we're going to do is we're going to figure out, all right, f double prime. Okay, so first off, we're going to find f prime. We have 12x squared plus 42x plus 36. Now, for the next one we're going to do is f double prime, because all of this, we're trying to figure out what f prime increases and decreases. So how do we do that? Well, we're going to take the derivative of f prime to help us determine our critical numbers of f prime. So what we have here then is going to be 24x plus 42. And now to find our points of inflection, we're going to take f double prime and set it equal to 0. And also we're going to determine, or we're going to figure out where f double prime does not exist. Okay? Now in this case, we're not going to use it does not exist because it's polynomial and all the values are going to exist here, but we can find out where it equals 0. So we're going to do that. We're going to subtract 42, divide by 24, and we get x. We can simplify this a little bit. Take out a 8, we have negative, not 8, what a 6. All right, when we do that, we have 7, and then right there is going to be 3, negative 7/3. So when x equals negative 7/3, that's where we have a possible point of inflection. And looking at our graph, that's where we can see that, yeah, it does look about like negative 7/3. So I'm guessing this is where x equals negative 7/3. That's where our point's going to be. So now, what do we do next? Well, just like when we use the first derivative test, as you're familiar with that, we need to test out to see, all right, where f prime is increasing or decreasing. So we're going to do a sign chart. We're going to take our, all right, possible point of inflection, all right, negative 7/3, and we're going to test it by going and creating intervals, negative 7/3 to infinity, and we're going to test f double prime. So testing f double prime, we're going to plug a value between negative 7/3 and a negative infinity. So I don't know, let's take like negative 3 when x equals negative 3 will work out? Yeah, 3 will work out. All right, so we have that. Negative 3. Plug in negative 3 times 24 is going to give us a value that's greater than 42. All right, so what we have is that's going to give us a sign of a negative number. So plugging this into our second derivative, all right, we realize we have a negative number. The next part is we're going to take a value here, so let's just take 0. Plugging this value into our derivative, okay, our second derivative. So f double prime of 0, that is going to be plugging in there. We realize we have a greater than 0, so it's going to be positive. And just so you know what we did over here, we took f double prime of negative 3, and we realized that we had a negative value, so negative. So what does that mean? Well, that means that right here, f prime is decreasing, right? That means that f prime is increasing because f double prime is positive. And because f prime is decreasing and f prime is increasing, we know that f is going to be concave down on this interval and then concave up here. We also see that there's a sign change. Because of the sign change, we know that at x equaling negative 7/3, we have a point of inflection. So up here, we can now write and finish all of our statements. So from negative infinity to negative 7/3, that is going to be concave down. So from negative infinity, oops, I want to write that properly, change the color. All right, negative infinity to negative 7/3, we're going to have concave down. And we verified that looking at our graph. It is concave down, all right? And then we know it's going to be concave up, all right, concave up, all right, from negative 7/3 to infinity, all right? And we see that right there, negative 7/3 to infinity, all right? And that's where it's been concave up. We know our point of inflection is going to be located at, all right, x equaling negative 7/3. And then if we plug in that negative 7/3 into f, we can figure out the y values, but that's our point of inflection. That's what we got. Why are all this taking place? Because we just justified our answer. We know that we have concave up, f is concave up, where f double prime is positive. That's why we're using the second derivative. All right, because that's where f prime is increasing. We know we have concave down because that's when f double prime is negative. That's what we're looking for, all right? And that's when f prime is decreasing. We know we have a point of inflection because we realized using our sign chart that we have a sign change for f double prime. And that's our first example. So you can see graphically, all right, you can see analytically how we determine the concave up and concave downness of a function, or concavity, I should say, of a function. All right, so that was our first example. We're going to go through some more in just a little bit. So I hope this helps you out on how to identify points of inflection of a graph, how to verify where functions are concave up and concave down, and also how to justify your answer.